small lecture using this worksheet that you can see here and introducing it with a little video. So I'm going to introduce the video, go over the worksheet and sort of mini lecture and example problems I did on Friday.
If they don't, it might be time for a new model. We've had lots of very different models for atoms since Democritus in 400 BC, and there will almost certainly be many more to come. Okay, tangent over.
Go back.
And there will almost certainly...
The Bohr model is the model that we did with circles. So we had a circle and electrons, and that circle was called an energy level, and then we had another energy level, and we put more electrons on. And the number of electrons that we put on, the total number of electrons we put on, was related to the atomic number. So if the atomic number is 4, then there are 4 dots. In this model that we're going to do soon, it's called the quantum model. And these clouds or orbitals are just places for electrons to be. And so each one of these little figures is just an area where an electron exists. And that's what most of this video is about.
Maybe many more to come. Okay, tangent over. The cores of atoms tend to stick together, but electrons are free to move. And this is why chemists love electrons. If we could marry them, we probably would. But electrons are weird. They appear to behave either as particles, like little baseballs, or as waves, like water waves, depending on the experiment that we perform. One of the weirdest things about electrons is that we can't exactly say where they are. It's not that we don't have the equipment, it's that this uncertainty is part of our model of the electron. So we can't pinpoint them. Fine. But we can say there's a certain probability of finding an electron in a given space around the nucleus. And that means that we can ask the following question. If we drew a shape around the nucleus such that we would be 95% sure of finding a given electron within that shape, what would it look like? Here are a few of these shapes. Chemists call them orbitals, and what each one looks like depends on, among other things, how much energy it has.
So, to reiterate, these are spaces in which an electron can exist if you're looking for it. So I wouldn't look for an electron in this orbital out here, because I would be unlikely to find it. I would look inside this space right here if I was looking for an electron in this orbital.
The more energy an orbital has, the farther most of its density is from the nucleus. By the way, why did we pick 95% and not 100%? Well, that's another quirk of our model of the electron. Past a certain distance from the nucleus, the probability of finding an electron starts to decrease, more or less exponentially, which means that while it will approach 0.
So, again, still reiterating, here's the 95% place to find an electron, and there's a possibility, 5%, that it'll be outside of that area.
Will never actually hit 0. So in every atom, there is some small, but non-zero, probability that for a very, very short period of time, one of its electrons is at the other end of the known universe. But mostly, electrons stay close to their nucleus, as clouds of negative charge density that shift and move with time. How electrons from one atom interact with electrons from another determines almost everything. Atoms can give up their electrons, surrendering them to other atoms, or they can share electrons.
So the chemistry, all chemistry is related to electrons, which is why we want to understand electrons. So in this, these notes, we are talking about energy levels again. So how big things are. So we could have this small sphere, and then we could have another sphere And that sphere is bigger, and then my number would get bigger. So we still have the numbers 1, 2, 3. We're still doing the same Bohr model idea with energy levels with this number. So this is the number part of the electron configuration. There's a shape part, and the shape can be S or P or D. And those shapes are that probability area where the electron exists. Some of these orbitals have different orientations. So this one is along the x-axis, and this one is along the y-axis, and then this one is along the z-axis. And I always say this is the ability to fill that space, that energy level, requires 3 different ones of these. And then the last sort of quantum idea is that you're going to, each of these orbitals, each one of these pictures can contain 2 electrons somewhere inside this space, but they have to have a property called spin, and those spins have to be different. So a spin, we say a spin up, and we designate that with an up arrow, or a spin down. There's only 2 choices, just like there's only 2 charges, a positive charge and a negative charge. All right. So let's do, what's all this mean? We're going to use, we're going to fill in every electron, and every electron has an energy level, it has a shape, an S, a P, a D, it has an orientation, and it has a spin. So every electron is different, and an orbital diagram maps out all of those different electrons that exist for an atom. There are 3 rules. The first rule is always start at the bottom. The second rule is you can only put 2 electrons into each orbital, and we represent an orbital with a line. And the third rule we'll get to in just a second. So what this means is we have 3 electrons. We have to start at the bottom. That's the off-bow principle. And we do an arrow up, and we do an arrow down. That's only 2 electrons, and then we do a third arrow up. So by convention, we do arrows up and arrows down. Let me try and redraw that so it looks nice. Now, I have drawn arrows that are these little half arrows, and this is a better arrow, and this is a better arrow. But because I'm going to be doing so many arrows, we choose to do these little half arrows when we're drawing lines. So that's all it represents. And one more thing. Before we used to do dots as electrons, which probably made a little bit more sense. But now we're doing arrows as electrons. So each arrow represents an electron. Okay, so what you do is you start at the bottom and then you move up. So for magnesium, we start at the bottom. And that's 1, that's 2, that's 3, that's 4, that's 5. So right here, where there are 3 lines all at the same distance from the bottom, or distance from the top, that brings up Hund's rule, which says whenever you're doing S or P orbitals, you're going to have more than 1 orbital, and you have to have the same spin before adding an opposite spin. So what that means is for each of these, as I'm adding them, they need to go up before you add it down. Okay, so well, it turns out that 2, 4, 6, 8, 10, I need to get to 12, so I need 2 more. So 1, 2. All right, let's do our last one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so now we got to follow this rule of putting electrons in 13. So I'm just going to stop here for a second because I had a lot of people questioning what was happening. So remember, I'm at 13 electrons. So if this was aluminum, which had 13 electrons, I would stop here. And I've been following the rules, but a lot of students are like, but you're leaving 2 of the orbitals blank. And it turns out that's okay. You can leave orbitals blank if you run out of electrons. And if I got to aluminum, I would have run out of electrons, and so I'd have these 2 blank ones. All right, continuing. So 13, 14, 15, 16. So I'm going to have 1 down and 3 up in my p orbitals. All right, great. I'm just going to do one more thing here, and that's to connect it back to the electron configurations. So when we did electron configurations, we would get to the end of a row, and in this case, wasn't ready for this. I'd go to the end of row 2 to get to sulfur, and that'd be neon. That didn't work. Oh, I know why. Well, fudge. Drat. Okay, sorry, I have to get out of this, which means I just erased everything. That's why I was saying drat. Okay, so when I get to the end of row 2, I'm at neon. And that means that everything was filled up because I'm going on to row 3. So when we did electron configuration, we said, oh, we're going to have neon. Remember, you can only do noble gases. And then after that, 10, 11, 12, 13, 14, 15, 16. After that, we had a 3s orbital with 2 electrons in it, and we had a 3p orbital with 4 electrons in it. And so that's how these are connected. This is like the full-on mapping out of electrons, and then this is the shorthand of it. All right, let's do one more just to make sure you get it, and then I'm all done. And that's good because people are coming. This is a nice way to remember everything. We're going to go right here to arsenic, which is number 33. And you'll notice that in order to get to arsenic, we had to get all the way to row 4. So that means that row 1 and 2 and 3 were all filled in. I don't have to follow any rules. All I have to do is fill them in until I get to row 4. And in fact, I'm going to fill in the beginning of row 4. And I'm actually going to go all the way through my transition metals. That's what these are. And then do rows down. And we're going to count them really quick. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So we're at 30 electrons. So there's 30 electrons right there. And how many more do I need? I need 1, 2, 3. So here in the p orbital, I need 3 more electrons. 1, 2, 3. And that's how you do it. And then if you wanted to do electron configuration, the end of the 3rd period is right here. That's argon is at the end. And so if we wanted to do arsenic, we would do argon. And then the 4s has 2 electrons in it. The 3d has 10 electrons in it. And the 4p has 3 electrons in it. All right. Hopefully that was enough to get you going. I'll put the worksheets at the end of the video, and I'll put the video as part of the lesson. Thanks. Bye.